Here guys, Mr. Carlson here. Let's talk about ions and how we write electron configurations for those. And then we're also going to look at photoelectron spectroscopy. For the first part here in your notes, when an atom gives up or gains electrons, it becomes what we call an ion. So anytime an atom gets a charge, basically, we refer to that as an ion, and this happens when the valence electrons are either gained or they're lost. So there's two ways that an atom can become an ion. They can either gain electrons or they can lose electrons. So if we look at fluorine right here, here's fluorine's electron configuration. It has a total of 9 electrons, 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 5 electrons in the 2p orbital. And what can happen is that fluorine, when it ionizes, or when it becomes an ion, it will gain an electron. And so if we look over here, I now have an extra electron in that 2p orbital. And so when we write this symbol for when fluorine ionizes, or when it becomes an ion, what we do is we would write the symbol, and then we're going to put a little minus sign up there. By the way, the reason it gets a negative charge when it gains an electron is because remember that electrons have a negative charge. When fluorine is neutral, it has the same number of electrons as it does protons. And so it has 9 positive charges in the nucleus. It has 9 negative charges in the electrons, and so it cancels out. It's neutral. But when it gains that extra negative charge, it now has 10 negative charges, 9 positive charges, and so overall a 1 minus charge, so F minus. For lithium, here's the electron configuration for lithium. I've got 1s2, 2s1, and for lithium, it's actually going to lose this electron right here, and when it loses that electron, this entire sublevel goes away, and we drop down to 1s2. When we lose electrons, we become positively charged because now, since I've lost a negative charge, I now have one more positive charge in the nucleus than I do negative charge coming from the electrons. So it would be Li plus 1 charge. For the electron configurations, let's take a look at aluminum 3 plus, meaning since it's a positive charge, that means it has lost 3 electrons. So we're going to write the electron configuration for aluminum minus these 3 electrons, basically. So remember, when we're writing these electron configurations, we're using the periodic table to do that. Aluminum would be right here on the periodic table. So following that along, it would be 1s2, 2s2, 2p6, 3s2, and then 3p1. So let's come back over here and we'll write that out. So 1s2, 2s2, 2p6, 3s2, and then 3p1. It's going to lose 3 electrons. Remember, the electrons that they lose or gain are coming from the valence shell. So I can't just take electrons out of any energy level here. It has to be out of the valence shell. The valence shell is the last energy level. So my last energy level is the 3rd energy level. So 1 electron out of that p sublevel, and then these 2 electrons, that's a total of 3. So this entire 3rd energy level is going to go away. And so my electron configuration for the aluminum ion would be just 1s2, 2s2, and 2p6. Notice that this electron configuration is the same as a noble gas. So if for aluminum it loses those 3 electrons, right? It loses 1, 2, and then another one, it goes to the previous noble gas here. Because remember, all elements want to get to this point in the periodic table. That's why they gain or lose electrons, because they want to get that full outer shell of electrons. They want to have that full valence shell, which is 8 electrons. And so if they can get to this point right here, they will be very stable, and so that's why these elements are either gaining or losing electrons to get to this point. Let's come back to this. So for sulfur, let's come back to the periodic table. Sulfur would be right here, so kind of close to aluminum, but it's right here. So let's write out the electron configuration for that. That is going to be 1s2, 2s2, 2p6, 3s2, and then 3p4. Now for sulfur is going to end up gaining 2 electrons. And what I want us to understand here is why sulfur is gaining electrons and why aluminum is losing electrons. So remember, they all want to end up at this point on the periodic table. For sulfur, it's close enough over here that it's going to be easier for sulfur to try to gain 2 electrons to get to this electron configuration here. It would be harder for sulfur. It would have to lose 1, 2, 3, 4, 5, 6 electrons in order to get back to this point here. So it's going to be easier to try to gain 2 electrons instead of losing 6 electrons. Both processes are going to take energy. It takes less energy for sulfur to try to gain 2 electrons. Aluminum, on the other hand, it's going to be easier for aluminum to lose 3 electrons instead of trying to gain 1, 2, 3, 4, 5 electrons, right? So that's why these metals over here and some of the metals right here like aluminum, they're going to form those positive ions because it's easier for them to lose these electrons, as opposed to these nonmetals that are over here. They're going to form those negative charges because it's easier for them to try to gain those to get to this point in the periodic table. Anyways, coming back to here. So here's our electron configuration for sulfur. It's going to gain, we said, 2 electrons. Those 2 electrons are going to go in this 3p sublevel. Remember, the p orbitals can hold up to 6, and so those 2 electrons are going to go in here, and my electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6. And again, this electron configuration would be the same as, I can't remember what it was right here, argon, I believe, is right here. And just by adding those 2 valence electrons. For zinc, this is the one I cannot remember. I believe zinc is right here on the periodic table. And so if we were to write the electron configuration for zinc 2+, let's do the noble gas configuration because I don't want to write out the full one here. So we said that this one would be argon. So we're going to go argon in brackets. And picking up from there, we're going to go 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 4s2, and then 3d10. Now, this is zinc 2+. It's going to lose 2 electrons, right? Well, is it going to pull those electrons from these d orbitals or from the s orbitals here? And remember, it's the valence shell that these electrons are being lost or gained. Now, for the transition metals, as we'll see, sometimes they will lose some of these d electrons as well, but they're first going to lose this the 4th energy level first, because this is the valence shell, that's the outer shell. So they're going to lose these first before they start losing these electrons. So for zinc 2+, that means these 2 electrons are going first. And so my electron configuration for zinc 2+ would be argon and then just 3d10, because now this has gone away after it loses those 2 electrons. So 2 atoms with the same electron configuration, we would refer to that as isoelectronic. Isoelectronic. So if I look at this, I've got 1s2, 2s2, 2p6, 1s2, 2s2, 2p6. We already said up here that's the same as which noble gas was it? for fluorine. So fluorine is right here. This would be neon. It would have the same electron configuration as neon. Or if I have 1s2 and 1s2, so Li plus 1, so let's come back up here. We've got lithium, which would be right here. Plus 1 meaning it's lost 1, so it drops back down to this noble gas, which is helium. So isoelectronic with helium. Let's look at these practice problems right here. Identify an ion of oxygen, that is isoelectronic with neon. We've kind of already talked about that, but here's oxygen right here. So oxygen is going to need to gain 2 electrons to have the same electron configuration as neon, right? So the ion of oxygen would be O, and then we're going to put 2 minus, meaning that it's going to gain those 2 electrons to have the same electron configuration as neon. Identify an ion of nitrogen that is isoelectronic or the same as O2 minus. So let's come back to this periodic table here. Nitrogen is right here on the periodic table, so one to the left of oxygen. Well, if oxygen had to gain 2 to get right here, and I want the ion of nitrogen that is the same as that, well, I'm just going to count how many electrons that it takes for nitrogen to get right here, which would be 1, 2, 3. So N3 minus is isoelectronic with O2 minus, which is isoelectronic with neon, right? They would all have the same electron configuration. They would all end basically with 2p6. Now, how do we know an atom's electron configuration? We use what is called PES, or photoelectron spectroscopy, or photoelectron spectra. Basically, it's a machine that kind of ionizes elements. It passes that element through magnets, essentially. And so, like if we had something like this, that where we ionize an element, we pass that through kind of like this curved chamber, and within this curved chamber here, we've got some magnets within here, and as those particles pass through, they're going to hit a plate, and depending on how big they are, some of those particles, like the bigger ones, they won't be as curved as easily by this magnet, and so they'll kind of maybe end up over here. And then the smaller particles, as they pass through, since they're smaller in mass, they get more affected by those magnets, and so maybe they end up a little further over here. And so as these particles pass through, what we get is kind of a readout for that, and that's what's shown right here. And if we look, we get some peaks at some different points on here. If we look at this graph on this, on the y-axis here, we've got relative number of electrons, and on the x-axis we have something called binding energy. That's basically, we can think of the binding energy as how tightly held those electrons are. So the higher the binding energy, the more tightly those electrons are held onto. And so if I think about this, if I look at these numbers here, notice that the higher numbers are actually closer to this axis. And we can think about this right here, this point on this graph, as being like the nucleus. And so really these peaks that are closer to this axis are the ones that are closest to the nucleus. And so if I think about my electron configurations of like that 1s, 2s, 2p, this peak right here would have to be the 1, this would have to represent the 1s orbital, because it's the one that's closest to that nucleus. And it would make sense that it would have the highest binding energy because it's, again, closest to the nucleus, right? It's closest to the pull of those protons. And then if we look, we keep going over here. The second peak would represent the 2s, right? Because that would be the next in energy. This next peak here would represent the 2p sublevel. And then if we keep going from here, looks like there's one peak right here. That would have to be the 3s orbital, right? And notice how the height of the peaks matches with what we've been saying about these electron configurations. So if we look at the relative number of electrons, if I look at the 1s, which remember can only hold 2 electrons, it goes up 1, 2. Same thing for the 2s, can only hold 2 electrons, 1, 2. The 2p sublevel can hold up to 6, 1, 2, 3, 4, 5, 6. And then we've got the 3s, which can only hold up to 2. So the heights of the peaks represent the number of electrons. And this would be a common question on the AP exam. They'll give you a blank PES readout like this, and they might ask you, they won't label this 1s, 2s, or anything like that. They'll just ask what is the element that is represented by this. And so again, what you'd have to do is label these out and count up how many electrons you've got. So if we look, we've got, lower this down a little bit, we've got 1s2, 2s2, 2p6, and then 3s2. So if we come to our blank periodic table, let's see, 3s2 would be right here. I believe that would be, if I remember correctly, would be magnesium, would be that one right there. And so this readout represents magnesium. Let's go to the second page here. So here's another photoelectron PES readout. And so this one again is saying identify the element represented here. So what we would do is, so I've got my 1s2. Let's write it out down here actually. So 1s, this goes up 2. I've got 2s2, and then this would have to be the 2p. So 1, 2, 3, 4, 5. So 2p5. Come to our thing here. So 2p, 1, 2, 3, 4, 5. So that would be fluorine. Whoops, wrong screen. So this would have to be fluorine. Sodium has a total of 4 peaks in its PES spectrum. So if we were looking at one of these, but only for the element sodium, it says it has 4 peaks. Their energies are 0.5, 3.67, 6.84, and 104. Which energy corresponds to the 1s sublevel? Remember that the 1s is the one that is closest to the nucleus, and so it has the highest binding energy. It's going to be the one that is most tightly held onto by the nucleus. And so if we look at these binding energies, it's definitely going to be the one that is the highest, right? So the 104 is going to be the 1s sublevel. Explain why there are 4 separate peaks in a sodium spectrum. Well, if each peak represents the next energy level, basically, if we come over here, sodium would be would be right here, actually. And so if we think about why is it do we have, for sodium, why do we have 4 different peaks? Well, we've got the 1s would represent one peak, the 2s would represent another peak, 2p would represent the third peak, and then I get to the the 3s sublevel, so that would be my 4th peak. So it has to do with all of the different sublevels. Whoops, I keep going to the wrong screen here. So to explain why they have 4 separate peaks, we could say that there are 4 different sublevels. Whoops, sublevels, and we could list those out. We've got the 1s, 1s2, 2s2, 2p6, and then the 3s1, because that's where sodium would end. And so there's our 1, 2, 3, 4 different peaks that we would see on our photoelectron spectrum. Suggest the specific sublevels that correspond to each peak. We kind of already did that right here. We said that the 104, the one with the highest binding energy, would have to be the 1s. The next one in line would have to be the 2s, then the 2p, and then the 3s, which would be the farthest away, so it's the one with the least binding energy. which peak would you expect to be the tallest or the greatest intensity, or in other words, the greatest number of electrons? And from our electron configuration, that would have to be the 2p sublevel. The 2p would have the highest intensity because it would have the most electrons. And that's where we'll stop for the notes today.